All right, let's see. So this is the first video for the last week of content that we're going to cover. We've got this one handout. I'll do the first half of the handout on this video. We'll do the second half of the handout on another video. And then we'll have a third one that'll cover another handout that I'm going to do. And then that's going to be it, okay? So let's see here. So here's the formula for the Taylor series. We've got the sum as n runs from 0 to infinity, f, the nth derivative of f evaluated at a divided by n factorial times x minus a to the n power. And I used n in this case so that it would match what was on the handout. So let's take a look at problem 2 here. We're looking at cosine 36 degrees with a equal to pi over 4 and n equal to 2. All right, so we need to go up to the second derivative. Our function is the cosine function. So our first derivative is negative sine of x, and our second derivative, negative cosine of x. So now we need to do f of a. So that's the cosine of pi over 4. I'm going to use 1 over root 2. That's a nice compact value, and it's an exact value. It doesn't lose any accuracy. If you're partial to decimals, well, this is not a bad approximation. It does go 5 places. If you're going to be using decimals, I would encourage you to take 6 or 7 places, because often our error will be in the 4th or 5th place, and if you're rounding to 2 or 3 decimal places, that's just going to throw everything off. Okay, so there's our f of a, 1 over square root 2. F prime of a is negative 1 over square root 2, and then f double prime of a is likewise negative 1 over square root 2. So for our second degree approximating polynomial, we'll have 1 over root 2 minus 1 over root 2 times x minus pi over 4 minus 1 over root 2 times a half times x minus pi over 4 all squared. Okay, so first thing we need to do is take this 36 degrees and turn it into radians. Okay, now you could multiply it by pi over 180 and you will get some decimal value. Okay, and again, if you're going to do that, take a good 6 places out of that decimal value. One thing I like to do is just multiply it by 1 over 180, have the calculator turn it into a fraction, and so you'll see this is actually going to be pi over 5. 36 over 180 is actually 1/5, and so in terms of radians, 36 degrees would be pi over 5. So as we're plugging this in here, we're going to be doing pi over 5 minus pi over 4. I'm just going to store that. Let's see if you get that little arrow there on the calculator. I'm going to store that as the letter A. So let's see here. Pi over 5 minus pi over 4. And so let's see here. So there it is. So now it's stored as the variable a, and then when I go to type this in to make our approximation, I can just do, let's see here, 1 over root 2 minus 1 over root 2 times a minus 1 over root 2 times a half times a squared. Okay, so let's see what we get here. Minus 1 over square root 2 times a, and then minus 1 over square root 2 times 0.5 a squared. Okay, so here's what that looks like on the calculator. Okay, and we get about 0.809455 or so. And let's see here. And we don't really, I'm not asking you to find the error or to see how close your approximation is. But if you go in and you find cosine of, let's see here, pi over 5, all right, then that's 809,017. So we've got a pretty good approximation. And like I said, our error is there in the 4th decimal place, in the 10,000ths place, and that's why it's important that if you're going to be using decimals in this process to go at least 6 or 7 decimal places before you look to round. Okay? All right, so there's problem 2. Let's look at problem 4. Okay, problem 4 is e to the 0.2, a equals 0, and n equals 3. Something that is interesting about what I just did there, where I used the calculator to see how close our polynomial approximation was to the actual value, is that phrase, the actual value, is a little misleading, because this cosine pi over 5 that I've typed in down here at the bottom of the screen, all the calculator is doing there is it's taking a longer approximating polynomial. Okay? It's taking an approximating polynomial that's long enough to give us, let's see, 4, 6, 8, 10 digits of accuracy. And then it just stops. It's just a better approximation. Okay? These numbers are constantly being constructed and approximated through the use of these Taylor series. Okay, so I think trying to think about that may give you a different perspective on using your calculator and what we do mathematically. Okay? All right, so our function here, f of x, is e to the x. And so that makes this nice and easy, because f prime, f double prime, and f triple prime are all also e to the x power. And so if we do f of a, then that's e to the 0 power, which is 1, and that'll be the same for f prime of a, f double prime of a, and f triple prime of a. They're all going to be 1. All right, so our approximating polynomial, P3, is going to be 1 plus 1 times x minus 0 to the first power, plus 1 over 2, x minus 0 squared, and then 1 over 3 factorial, x minus 0 cubed. So this is a nice, straightforward approximating polynomial. We've got 1 plus x squared over 2 plus x cubed over 6. And now we want to evaluate this for 0.2. All right, let's see what we get here. So 1 plus 0.2 plus 0.2 squared over 2, and then plus 0.2 cubed over 6. And this gives us about 1.2213 repeating. So that is an exact value. And let's see here. What is a better approximation for e to the 0.2. This is approximately 1.22140, dot, dot, dot. Okay, so we've got a pretty good approximation on this one. And there's the approximate value with the cubic approximating polynomial, and the better approximation coming from the calculator, doing e to the 0.2 power, accurate to 10 decimal places. Okay, let's see here. We'll look at a couple more here. So, problem 6 is cube root of 10. We've got a equal to 8 because that's a nice perfect cube. And what else? N equal to 2. So our function, f of x, is the cube root function, or x to the 1/3. So our first derivative, 1/3 x to the negative 2/3, and our second derivative, negative 2/9 x to the minus 5/3. Okay, f of a then is going to be 8 to the 1/3 power, the cube root of 8, which is 2. And this is kind of the purpose of that a value, is that if you want to make an approximation, choose something near it that's easy to calculate, and then these subsequent terms will adjust the value of this to try to approximate the value that you've got inside, that you're looking to find the cube root of. All right, let's see here. F prime of a is going to be 1/3, let's see, 8 to the negative 2/3 is going to be a 4 in the denominator, so that'll be 1/12. And then the double prime, let's see, negative 2/9 times, let's see, 8, 2 to the 5th power, 32 in the denominator. So this is negative 1 over 144. All right, so our approximating polynomial, I keep forgetting to erase those. Let's see, our P2 of x is going to be 2 plus 1/12 x minus 8 minus 1 over 144 times a half, which is 1 over 288 x minus 8 squared. All right, so if we want to evaluate this for 10, that'll be 2 plus 1/12 times 10 minus 8 minus 1 over 288 times 10 minus 8 squared. Okay, so let's see here. 2 plus 2 over 12 minus 4 over 288. And this comes out to be about 2.1527 repeating. And the actual cube root of 10 is approximately 2.1544 dot, 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 let's say. Okay, so there's the approximating polynomial calculation right there, and then the better approximation for the cube root underneath it. Now the calculator, when it's calculating roots, I don't know for sure that it uses the Taylor series. I'm pretty sure that for square roots it does not, okay? If we get a chance, I might talk a little bit about a common algorithm for calculating square roots that is frequently used. It's a lot less complex than the Taylor series, but the Taylor series is really necessary for things like calculating powers of e, doing sines and cosines, and so on. When it comes to cube roots, I'm not really sure what the calculator is doing. Okay, let's look at one more here. Look at problem 8. Problem 8, square root 50 take a to be 49 and n to be 3. All right, so our function here is the square root function, or x to the 1/2. So our derivative is 1/2 x to the minus 1/2. Second derivative, negative 1/4 x to the minus 3/2. And our third derivative is positive 3/8 x to the minus 5/2. All right, let's see here. So f of a is going to be 7. F prime at a is going to be what? 1/2 times 1/7, so 1 over 14. F double prime is negative 1/4 times, let's see, what is that? So that's going to be 1 over 7 to the 3rd power, 343, times 4. So this is negative 1 over 1372. And then this one is really kind of a mess. If you do it as a decimal, you're going to run into scientific notation. It'll be times 10 to the negative 5th, so you're going to wind up with 4 leading zeros. Let's see here, 3/8. So 49 to the negative 5/2 means that we're going to square root the 49 and then do 7 to the 5th power in that denominator. That's why this gets so large. So 8 times 7 to the 5th power, 134,456. 134,456. All right, so let's build our polynomial. P3. So we're going to have 7, and then 1 over 14, x minus 49, and then minus 1 over 1372 times 1/2, and so what is that? 2744, and then x minus 49 squared, and then this will be 3 over 134,456 times 1/6, right? Because it's got to be 3 factorial. So that'll go in twice, and I got to take that 134,456 and multiply it by 2. And so this will be 268, 912, x minus 49 cubed. Okay, now our x is 50. And so x minus 49 in all of these is just going to be 1. I'll put the 1s in there. All right, so let's see what we got. 7 plus 1 over 14 minus 1 over 2744, and then plus 1 over 268, 912. And so this gives us 7.071, 067, and the calculator, square root 50, 7.071, 0678. Let's see, how close were we? Did we actually get all 10 decimal places there? Oh, just about. So here it is. You can see on the calculator here. So it's actually good up to the 8th decimal place there. Okay? So not quite all 10 places of accuracy, but you can see how these things work pretty well. And like I said, I think that the calculators tend to use a different algorithm for the square root function because there is such a simple one available, and that'll save the calculating power for you doing the Taylor series for things that they really need. This whole question of algorithms is actually a really interesting and vitally important part of math and computer science. People are constantly working to find ways to program a computer to make a standard calculation in the most efficient way possible. So if you ever end up going on and taking courses in computer science and computer programming, you will become familiar with some algorithms. All right, so that's it for this video. I'll do the rest of this handout in another video, and we will see you then.